Okay, welcome to Intro to Quantum Field Theory, episode 28, Self-Interactions. It's been a while since our last episode, so let's catch up a little bit with two lines. Let's just recall the Klein-Gordon Lagrangian density, where you have the gradient of the scalar field squared, and then you have the minus the square of the mass term times the field squared. Now, we can also have Lagrangians with the following form. So we can also have Lagrangians that look like this. 1/2 partial mu phi partial mu phi minus 1/2 mu squared phi squared, then plus 1/4 factorial lambda phi to the fourth. We now have a new term. And this new term right here, this is a self-interaction term. Now we're going to look at Klein-Gordon equations. So recall that a modified Klein-Gordon equation, that is a Klein-Gordon equation with interaction terms, looks like we have the d mu, or partial mu, then plus mu squared phi equal to the derivative with respect to the field times some potential or some interaction term that depends on the field. In the self-interaction case, in the self-interaction case, we have that this interaction term is quite literally just the 1/4 factorial lambda phi to the fourth. Therefore, let's take the derivative of this quantity with respect to the field. So we have this 1/4 factorial lambda phi to the fourth. And we can bring out these terms here, phi to the fourth. This is just a simple bring the 4 down here, and then you end up with only a 3. So we get 1/3 factorial lambda phi cubed. Like so. So this implies that our modified Klein-Gordon equation looks like this: 1/3 factorial lambda phi cubed. Now, this is going to require us to use the general field solutions, where we sum over interaction terms in all possible locations in space. So recall, we're using a lot of the phrase recall. Recall the general field solution for this is the inhomogeneous for the inhomogeneous Klein-Gordon equation. And this is phi g x mu integral over space. Then the gradient or the derivative of this interaction term, which is a function of the general solution in this alternate position space, different from this position space, then times the special solutions, x mu, y mu. And so the form of our equation specifically will be as follows. We're going to forego the g subscript. So we're just going to get phi of x mu is the integral over this space, and then 1 over 3 factorial lambda phi cubed, where phi is a function of y mu, and then we get the special. But this is not ideal because this is a very, very difficult equation to solve, because the equation we're solving for, phi, is within the integral. So we need to try to solve this using a mathematical trick or technique called a perturbation. So we are going to look at a perturbation ansatz. So perturbation ansatz. And that is that we have to posit first that lambda is less than 1. That's the only way in which this works. Then we can say that the field is the sum over powers of lambda times different fields, different levels of field interaction. Or not field interaction, but different levels of fields. So this ends up looking like phi naught x mu plus lambda phi 1 x mu plus lambda squared phi 2 x mu, and you can continue going on. This is the perturbation ansatz. This is right here. We will see that this is the free field. This is the first order perturbation. And this is the second order perturbation. Okay. So let's plug this into the Klein-Gordon equation. So plugging this into the Klein-Gordon equation, I get partial mu plus mu squared phi equals 1 over 3 factorial lambda phi cubed. We have this, which then becomes, I'm going to just copy and paste this. And then I'm going to copy and paste this. Equals 1 over 3 factorial lambda this quantity cubed. Okay. Now we can expand out the right side a little bit. So when we multiply this 3 times, the lowest or not lowest order, but the leftmost term will be, we'll have phi naught times phi naught times phi naught. So phi naught cubed will be the first term. And then we'll have 3 iterations where phi naught is squared. So we get phi naught squared. We'll have phi naught times phi naught and then times phi 1. And we'll have that happen 3 times because there are 3 multiplications. So let's just erase these. We get 3 times lambda times phi naught squared phi 1. Likewise, there will be 3 times where we have lambda squared phi naught phi 1 squared. And then we're going to just end up with, continue ending up with higher order terms. Now what we do is we expand all the lambdas in here, because what we can do is that there's a different power of lambda for each term on the left-hand side, which means that we can equate. So the term here, that this will have no lambdas, so we can equate it with something here that has no lambdas. There's 1 lambda in this term, so we can equate this times this to whatever here is just times 1 lambda. And we can do that for every term. So we're going to now put this in and see how it looks so that we can actually expand this out term by term, or rather have a term by term equations. Okay, so the first one, no, shouldn't be cubed. The first one is quite simple. We just end up with this. And then here it becomes lambda squared, then 1 over 2 lambda cubed, and so forth. So different powers of lambda are equal. So different powers of lambda are equal. So we get partial mu plus mu squared, phi naught equal to 0. So this indeed is the free field, because there are no terms here that don't have lambda. So this must be equal to 0, which means this is indeed the free field. Continuing, we get phi 1. And phi 1 here just has 1 lambda, so just this term. So we get we get 1 over 3 cubed lambda phi naught cubed. Likewise, we can solve for the phi2 term. And the phi2 term has lambda squared. And the only thing here with lambda squared is this phi naught squared, phi1. So we get 1 over 2. Um, Actually, these lambdas cancel out on both sides, so we don't end up with the lambdas. So it's just phi cubed naught. And here it's phi naught squared, phi1. And this just goes on and on and on. And we can do the same thing with this. Give me 1 second. We can do the same thing with the solution, the general solution, which is z cubed y mu b s x mu y mu, like so. So these become the solution for phi1 is the integral over space of phi cubed of the free field, then at phi of s. And then here, this will have a factor of 1 over 3 factorial. This will have a factor of 1 over 2. Then you'll have phi naught squared, phi1, phi s. And so on and so forth. So let's kind of try to interpret what these phi naught cubed, phi naught squared, phi1. Let's try to interpret what these are in line with the phi s's here. So phi naught is the free field, which means that phi1, think about this way. Think about it like nodes. So we have node here and a node here. This particular node is the position in the what do you call it? The basis on the left-hand side of the equation using the x, and then y is looking at positions away from it. So you have some position, and then you're looking at every other position y different from it. And the object that connects those two positions in space, or that relates the information at y to the information at x, is phi s, the special solution. And then phi naught there are these interaction terms, self-interaction terms. So phi naught interacts with itself 3 times here at this position, and then phi s relates it to the other position of the field, and that gives you phi1. So then you can think about phi2 in a similar way. You can have this, except instead of this third self-interaction term, you then consider how another point in space, y prime mu, Consider how another point in space, which is connected by this special solution again. So this special solution now connects another point in space to this point in space. And there it says, okay, well, let's consider the three self-interactions here. So this just the first order approximation or perturbation looks at all the self-interactions in space at one location. Whereas for the second order approximation, it looks at the self-interaction terms at every location in space and how every location in space self-interaction term is affected by every other location in space um, self-interaction term. And you can see that this will just keep branching and branching and going on and on and on. And this is what the self-interactions um, look like, and this is what the calculations are computing.